Welcome back to our heat transfer class, where we're delving deeper into the fascinating world of the Mal energy exchange. This video was made with the support of Energy. Remember that the introduction to heat transfer is divided into several lessons. Let's continue with the second lesson about the energy conservation requirement. It aims to explain you the fundamental equation needed to build heat transfer mathematical models.
The mathematical models to calculate heat transfer problems are built departing from the conservation equation. Remember, start always the resolution of exercises thinking about how and where to apply the conservation equation. Let's address this principle using a day-to-day example. Imagine that you arrive at home in winter after a long travel and the house is in thermal equilibrium with the environment. The first thing you do is to start a fire in the biomass heating system. The amount of firewood consumed per unit time determines the rate of heating of the indoor air. After a long period of time, the temperature inside reaches a constant value. To avoid the temperature to decrease below the comfort temperature, you need to provide firewood continuously. The amount of firewood expended per unit time determines the value of the indoor air temperature. This is because there are heat losses through the ceiling, the walls, and the floor. In this specific case, also with the hot gases that come out of the chimney. Try to answer the following questions. How can you quantify the amount of firewood needed to keep the inlet temperature at a comfortable value? In addition, how can you calculate the time needed for heating the house? Stop his video here and try to answer these questions. The answer is by using the energy conservation equation. This is done by defining first a control volume. The next step is to identify the different energy terms. We will define them as energy per unit time. The internal generation of energy per unit time, e.g., is due to the conversion of any other form of energy, such as mechanical, electrical, chemical, nuclear, or electromagnetic, into thermal energy. In the example of your house, the combustion of firewood is a conversion of chemical energy into thermal energy thanks to the enthalpy of the combustion reaction. When evaluating inputs and outputs, it is essential to analyze if there is a flow of mass throughout the surface of the control volume. In your house, there is an input of air at ambient temperature and there is an output of hot gases in the chimney. In this example, the only input is the enthalpy of the ambient air used for biomass combustion. The hot gases of combustion represent an output of energy. Other energy outputs are caused by heat losses. In the transient state, the difference between the sum of inputs plus generation minus the outputs can be positive or negative, never zero. This difference is the amount of energy stored inside the control volume per unit time. In the steady state, the stored energy per unit time is zero. This allows defining more accurately the steady state. The variation of the energy stored in the control volume can be a variation of the internal, kinetic, and potential energy. In heat transfer problems, the variation of internal energy is much larger than the other two components, so we will only consider variations of internal energy. This variation can be sensible heat, when there is a temperature variation, or latent heat, when a phase change is experienced at constant temperature. For processes without phase change, the variation of stored energy per unit time will produce a variation of the temperature over time within the control volume. The energy conservation equation can also be applied in surfaces. Because the surface has no mass or volume, there is no internal heat generation or energy storage. Therefore, the energy inputs per unit time are equal to the energy outputs per unit time. Whether a heat flux is an input or an output is something we will discuss when solving problems. With these tools, we can already start to solve heat transfer problems. However, what remains to be known are the rate equations that allow evaluating the heat transfer rate based on the difference in temperatures. Don't miss the videos about heat transfer mechanisms.